In this video, we'll talk about thermodynamic entropy. First, we need to define thermodynamic system. A thermodynamic system consists of many particles. The collective behaviors of all these particles are thermodynamic properties, such as energy, pressure, temperature, volume, and entropy. Thermodynamic entropy is a measure of the uncertainty of a thermodynamic system. More precisely speaking, entropy is a measure of energy dispersal, or how energy is distributed among all those particles, such as atoms, molecules, ions, and electrons. The equation for calculating thermodynamic entropy is very similar to information entropy. So if we compare the information entropy and thermodynamic entropy, the difference is minimal. We need to replace this log 2 with this natural logarithm, and we need a constant in front of the sum. This constant is the Boltzmann constant. Now the equation for thermodynamic entropy is expressed this way. However, on the tombstone of Boltzmann, we see a different equation for entropy. Entropy is equal to K times the logarithm of W. This is because if we can assume all W outcomes are equally probable, and then this probability is always equal to 1 over W. If we replace this p sub I with 1 over W, and this one also with 1 over W, and the number of outcomes with W, we have this expression. We can simplify the sum because we have W terms and each term is the same. So this sum is simply the logarithm of 1 over W. With this additional negative sign, the result is simply Boltzmann constant times the logarithm of W. This is exactly the same as this on Boltzmann's tombstone. Now, how do we calculate the entropy of a thermodynamic system? First, we need a zero reference. The entropy of a pure chemical at 0 Kelvin, the absolute zero temperature, is arbitrarily set to 0. And then the entropy of a pure chemical at a different temperature can be calculated based on the zero reference. Under 1 atm pressure, the entropy of 1 gram ice at negative 273 degrees Celsius is just 0. 1 gram of ice at 0 degrees Celsius is 2.7 joule per Kelvin. How about water? At room temperature, its entropy is 3.9 joule per Kelvin. If you have 1 gram of hot steam at 100 degrees Celsius, the entropy is 10 joule per Kelvin. As temperature increases, the entropy increases. When chemicals mix, we have additional mixing entropy. So if we mix 50 water molecules and 50 ethanol molecules, the total entropy of the mixture is greater than the sum of the entropy of the water and the entropy of ethanol. We have additional mixing entropy. We can calculate the mixing entropy using this formula. We just plug in numbers. N is the number of molecules. 50 plus 50, we get 100 here. K sub B is Boltzmann constant. And then we just need to sum up all those pi times the logarithm of pi. A molecule in the mixture can be water or ethanol. In this case, 50-50. So we just need to have two terms of 0.5 times the logarithm of 0.5. The result is this. Now let's calculate the entropy of a human brain. The mass of a human brain increases from 350 to 1400 grams in the past millions of years. How do we calculate the entropy of a human brain? So roughly, the entropy of 1 gram solid is 1 to 3 joule per Kelvin. The entropy of 1 gram liquid is between 2 and 4 joule per Kelvin. So if we sum up all the entropy of all substances of the brain, it's about 5,000 joule per Kelvin. But what about the mixing entropy? When we mix 1 million chemicals, the mixing entropy can be from 0 to 5 kilojoule per Kelvin. If we mix 1 trillion chemicals, the mixing entropy can be from 0 to 10 kilojoule per Kelvin. So we have an upper limit here. This upper limit is proportional to the logarithm of the number of chemicals being mixed. That's why when this number going from 1 million to 1 trillion, well, the entropy only doubles. Taking the mixing entropy into account, we know the total entropy of a modern human brain is 10 plus minus 5 kilojoule per Kelvin. What about a smaller brain? Well, the entropy of a pure chemical is proportional to the mass. The mixing entropy of many chemicals is also proportional to the individual masses, assuming the same composition. Therefore, the entropy of a smaller brain with 350 grams would be just 25% of a bigger one. The entropy of the human brain has quadrupled in the past millions of years.